Alright, so today we're going to look at relativistic momentum, part of the series of special relativity. The dot point we're covering today is describe the consequences and applications of relativistic motion or momentum using this formula here. Okay? And we're also going to look at the limitations as to why maximum velocity is imparted on a particle, because of what special relativity tells us. So, the actual formula, or if we actually have a look at this, we have relativistic mass. So Einstein argued that the mass of an object is dependent on its overall speed. Okay. There's a lot of different equations we can use. We already talked about how as objects move at the speed of light, time dilates, and there is length contraction. Similar thing we also find is that mass will also increase. So we know that based on his equations, mass will increase as you travel at the speed of light. So this is the actual formula, and this formula here represents the change in mass due to special relativity. Okay, so m0 is the proper mass, or you can call it the rest mass. So how much kgs does this object have if it was stationary? That's what m0 stands for. If the object is moving at really high speed, there will be some kind of mass increase, m. Sometimes you'll see it written in textbooks as mv, to represent the moving mass, so you could do that as part of your notes. But remember, this is all assuming we're moving at a constant speed or in an inertial frame of reference. Okay, so we know that the relativistic mass will change in accordance to a stationary frame. Now, let's actually look at this in terms of a graph. Okay, so we know that the overall rest mass at a very small value for V. So if V is very small, we can see there's not really much change. Okay, so the mass increase is very subtle. It's not until at least when you start to get to about 0.8, so about 80% of speed of light, will you start seeing a gradual increase in the mass. And then once you get to 90 and above, you'll see almost an exponential growth. And what we'll see, or what we predict, if we have a look, is when we get to 1, the mass is thought to go to about infinity. Okay? So as V gets larger, m, okay, or let's say as V goes to 1 c, speed of light, the moving mass will reach infinity. That's what the equation tells us. Okay, let's do some calculations here. We'll talk about what's the consequence of this exponential increase in mass. Give us a little bit of context on why we can't travel at the speed of light. So that's the important question here. Okay, so it says, what is the relativistic mass of an electron? We know that the electron's mass is that, and we know that it's traveling at this particular velocity. Okay, so the rest mass of an electron is 9.109, 10 times 10 minus 31, 1 over the speed of our moving particle squared over the speed of light. Remember, the speed of light is given in your formula sheet, so I'll always reference that if you're not sure. Final answer I get, if I round it off to 2 sig figs, is 1.1 times 10 to the power of minus 30 kgs. So it's still a very small mass, but if you actually compare it to the rest mass of an electron, we are an order of magnitude of 1 bigger than when it was not moving. Okay, so there's that. And then question 2, it says, what speed is a particle moving if the relative mass is 5 times larger than the rest mass? So we know that. So what we know is the moving mass is 5 times bigger than our rest mass. Okay, so our way of writing that, if we want to do so, is we can write like so. We can say that in comparison, our moving mass is 5 times bigger than our rest mass. Okay? Another way we can write that, I'll just show you again. So our moving mass is 5 times bigger. Okay? So that's what we have. Okay, so I'm going to use the equation above and I'm going to try and find a value for the speed. So just rewrite that equation here. And what I'm going to do is I'm going to write 5 in front of MO0 or M0 to represent that it's 5 times as much. Okay? Alright, so I want to find the overall speed, so I'm going to move this equation over. I'm going to do it in a slightly different color just so you can see where the working out is coming from. So we have mass. Actually, I'll change it to a different color. Not good. Alright, I'll just stick back to yellow. Alright, so we have mass. Now it's 1 minus b squared over c squared equals 5 of the initial mass there. Okay? So, if I move everything across, we have square root of 1 minus b squared over c squared, 5 proper mass over the mass there. Okay? So if you recall, when we did the equation, this is what we represented based on what we drew here. So if we have the inverse of that, okay, so if we have the inverse of that, then essentially it's the same thing as saying it's 1 over 5. Okay, because of the equation we wrote here. So if mv over m0 is equal to 5 because of what we wrote here, then m0 over mv is 1 over 5. So we're saying in comparison to mv, m0 is only a fifth of that. So let's rearrange our equation again. 1 over 5. Square both sides. Okay. Might be writing out of space actually. We'll keep going. So I'll add the 1 on the other side, and as you can see, there is a negative here. So I want to make b obviously positive. So in order to do that, hopefully I still have some space. Minus 1. Then I'll just rearrange that. It's 2. Okay. What I can do now is, just to make life a little bit easier for myself, I'm just going to continue on from this side. I do apologize for the lack of space. Okay, so I have the formula at this particular stage here. All right, so I can actually square everything. And then I move C over, so V equals to C, like so. Okay, so that's my final calculations. I'll find that it's roughly 0.9798 of the speed of light. So it's about almost, if you round it up to 2 sig figs, about almost 80% or 98% of speed of light. So that's how fast you can travel for that particular particle to have 5 times its original mass. That's what we're aiming for. Okay? Now let's look at in terms of momentum. So we already know that momentum, in terms of Newtonian physics, is mass times force. We know that because velocity has to stay constant if we're traveling at the speed of light. So this has to be a constant. What we talked about before with time dilation and length contraction is if that stays constant, the other two obviously has to change. We already know that there is a relativistic mass increase. We also have a relativistic momentum increase as well. Okay. We also know that another way to write momentum, or the change in momentum, is force times the change in time. Okay. Now time also has a relativistic effect, so time dilation. So we can actually combine these two equations using our understanding of the Lorentz factor here. We can actually create a new formula for momentum that encounters the special relativity effect. Okay, so we get that the change in momentum is force times change in time equals to mass times change in velocity. Okay, we know that time is not constant. So we're going to designate the starting point of whatever scenario we have as proper time. So delta T0, that's what we get here. We also know that mass is going to be the rest mass here, if we're basing off Newtonian physics. So we're going to denote m as m0 here. Okay, so we're just taking into account these kind of things here. So, according to a stationary observer, the time of this momentum experience will dilate. So there's time dilation here. Okay, we know that the formula for time dilation is this formula here. We just got rid of the Lorentz factor and put it as a constant. We rearrange the equation, that's what we get here. So we're going to sub this into here and see what we get from there. Okay? So, if we want to look at momentum in terms of special relativity, we've already equated that time is proper time, mass is proper mass, and we also got to substitute the time dilation formula into our equation here. Okay, what we'll get is this new formula here. So this is what we get. Okay. And what I'm going to do is I'm going to move gamma over onto this side. Right? So I have force times the change in time, but in this case, the time dilation, or time dilated. Okay? And so this is the formula I get here. Now, as you can see, because I've already considered time dilation in the formula, then what I'm going to get here, lowercase p, what I'm getting here is the momentum in terms of special relativity, or relativistic momentum. Okay? So, this is what I get. So I get that So this becomes change of P, or that is equal to gamma, and we know that m naught delta V is still the original proper momentum we were looking at. Okay, so that's the formula we get. Okay, so if we substitute the Lorentz factor out, we know that the Lorentz factor is this equation here. We get this equation. So this equation is for relativistic momentum. This is what we will see in terms of the momentum if we're in a stationary frame and we watch an object moving at the speed of light or near the speed of light. Okay, so that's the equation we have there. Okay, so m naught is the proper mass, and velocity is obviously that. That tends to be why in Syllabus we don't really use the mass increase formula, because it's part of the momentum formula. So that's another way to work out proper mass that way. Remember, you can rewrite the equation like so in terms of the rest frame momentum, or you can write it with the Lorentz factor. Okay, so that kind of tells you everything you need to know. So what are the consequences of relativistic momentum in terms of why would this equation tell us there's a limitation on the maximum velocity of a particle imposed by special relativity? Let's have a look, okay? We know here that as we get closer to 1, or closer to the speed of light, the overall momentum is going to rise up to infinity. Okay, so that's what we said here. Now there's a couple of things we need to talk about, and that's to do with force. Okay, so if we have a look with mass increase, so mass dilation or mass increase, we denote the formula as such. Okay, what I want you to think about is where we get this idea from with mass and Newton's law. So force is equal to mass times acceleration. Okay, so we know that in order to get something moving closer to the speed of light, let's assume we're applying a constant force. Okay, mass will increase, so it's going to continually to increase. To maintain a constant force, your acceleration will go down and closer to 0 as you get closer to the speed of light. So what that's saying to us is, if I have, let's say, an electron, and I want to move it at the speed of light, what we'll see is an increase in mass, so the mass of the electron will get bigger, but as it gets bigger, to maintain the same force of acceleration, or to maintain the same force applied to it, I need to apply more energy, okay? Because what's happening is, as the mass is increasing, the acceleration on this electron is decreasing. So it actually becomes more difficult, okay? So it becomes more difficult to accelerate as its mass increases. That's what the formula is showing us here, okay? Let's have a look at some other reasons, okay? So as the velocity approaches the speed of light, the relative momentum approaches infinity. There are two main consequences. We already talked about one, but let's go over it again. As the speed of the body approaches c, the mass and momentum approach infinity. Okay, so the mass and momentum go to infinity. Now, if we apply a constant force, F equals ma, that would imply that acceleration will go to 0. Okay, so this is constant. If this is going to go to infinity, this will end up going to 0. Okay, which means the closer we get to the speed of light, the more massive the object, the less acceleration there is on the actual particle, which means it's harder to push it faster. Okay? As the velocity of the body approaches c, the relative mass also approaches infinity, and thus the force continuously increases to maintain a large acceleration. Okay? So if we want to increase, let's say we can increase the force, because that's our only way to ensure that acceleration will increase. Okay? So what that means is we need an incredible amount of energy, and obviously that's not possible. You can't just get energy out of nowhere. So the final result of this is an object theoretically cannot approach the speed of light, or can't reach the speed of light, but it can get close to the speed of light. Okay? Because we're trying to find an additional amount of force out of nowhere. So that's not quite possible. All right, in terms of what we can see, this is Newtonian physics. If we were to look at momentum, if we looked at the special relativistic effects, we can see that momentum skyrockets around about 80% speed of light. At really low numbers or at really low velocities, it really doesn't matter about special relativity. The effects are so small, we can just ignore them. But as we get closer to the speed of light, we do have to pay attention to it. In terms of applications of momentum, so the force required to accelerate a particle at a constant rate will also mean that it does cost a lot of money to make the particles accelerate really quickly. What we also know is as the particle gets faster, it's going to increase in mass. So you need to obviously have a very small object, particle that is, to accelerate, because as you get closer to the speed of light, it will get bigger and it'll be harder to move it. So that's why they do use things like protons and stuff like that, subatomic particles rather than actual atoms. In terms of particle accelerators, another thing is sometimes they will be fired in a circular path. So what we also know with this is as the object has a mass increase as it travels closer to the speed of light, as this gets bigger, if we are applying a constant force again, okay, then that means that the radius will also decrease. So let's just go through this. A constant increase in speed means a huge amount of energy is required and the cost of developing and maintaining the equipment. So that's one of the things when you talk about particle accelerators. Particles' relative mass will increase and become harder to follow a circular path because you need a lot more force to keep it in check into the circular pathway there. There are some calculations for relative momentum. I'll go through them in another video. But that's basically that, to explain all you need to know with relative momentum. Hopefully that makes sense. If not, obviously look back on it again.